In the previous lectures, you were able to understand how a two-dimensional NMR experiment is very helpful. And in particular, we paid attention towards how the correlated spectroscopy experiment helps you get correlations between protons that are scalarly coupled with one another. Similarly, we also were able to take an example where the 2D jail resolved experiment helped you provide the multiplicity and the magnitude of proton-proton coupling from the indirect dimension for two protons that are scalarly coupled with one another. The immediate question that comes after this is whether a similar two-dimensional NMR experiment could be performed between different nuclei. For instance, can it be performed between carbon-13 and 1H? From the penultimate lecture, I'm sure you would be able to remember that such correlated spectra were indeed shown and therefore they are indeed feasible. In this lecture, we will take a closer look at how this is possible and how can one generate an experiment of that sort. So to begin with, let's look at an experiment called the HSQC. HSQC stands for heteronuclear single quantum coherence spectroscopy. So HSQC spectrum indicates that you will be exploiting the single quantum coherences that are generated to get the correlation between two heteronuclei. For instance, carbon-13 to 1H or 15N to 1H or even 13C to 15N, just for an example. This experiment actually begins with a module that we have seen in detail in the previous lectures, that is the INEP module. So I'm just going to write it as 1H and X channel, where the X could be C13 or 15N. As you might remember, the first and the third pulse in the proton should be orthogonal to one another. So if the first 90 is applied along X, then the second 90 that comes in the proton will have to be applied along the Y phase. So now in this experiment, what follows this would be something called T1 evolution, the 180-degree pulse applied along the proton channel exactly at T1 by 2 duration, followed by an INEP that goes back to proton, and then you would detect in the proton dimension with carbon being decoupled. Once again, so this is a variable delay T1 and T2. T2 is direct dimension acquisition. Well, the tau delays, if you might remember, were set to 1 over 4J, where J is the J coupling between the CH spin system that you're trying to look at. CH or NH, remember this could be any of the correlated spectrum that you're trying to achieve here. There are a few important aspects that I would like to show first before going to the product operator formalism. You excite the proton nucleus and you detect also in the proton nucleus. This is important because the signal to noise ratio is proportional to the first power of the excited nucleus and 3 by 2 of the detected nucleus. This ensures that you get the maximum sensitivity for such two-dimensional NMR experiments. In addition, if you might remember, the recycle delay which is required to get the steady state magnetization now will be determined by the proton relaxation. Generally, it is known that the T1 times of 13C and 15N is much greater than that of T1 times of proton. So therefore, you would be able to repeat the experiment much quicker for waiting for a shorter duration of the recycle delay. Okay, the first set of steps out of the way. Let's begin with the magnetization along the proton. Then if you are applying the INEP module, I'm sure you might recollect where the tau is set to 1 over 4J, you would create something of this sort. Of course, after this 90 pulses what I'm writing, let's take for an instance, we are doing carbon experiment. You ended up generating CX. So now when you have the T1 duration, there are a few set of parameters that will operate. You have the carbon chemical shift, you would have the proton chemical shift, and you would also have the 2 pi j head z term. Let's go back to the pulse program and look at this end of the module. The first thing that comes to your head is that head z will commute with head z, so the proton chemical shift will not evolve. And you have a tau 180 tau module such that proton chemical shifts ends up refocusing. And you have scalar coupling. I would like you to recollect, so if you had a module of this sort and you have two head z cx, kindly go back and do the product operator formalism where the 180 pulse is only on the proton you would realize that the scalar coupling will also not evolve. So this 180-degree pulse achieves the purpose of decoupling in the F1 dimension. Since you're measuring chemical shifts on the T1, this will help you get decoupling in the indirect F1 dimension. And following this, what you end up understanding is that only the chemical shift of carbon ends up evolving. So for that matter, if you have 2HZCX, when you are trying to evolve carbon chemical shift, what do you end up getting? You get 2HZCX cos omega C T1, omega should be the offset, plus 2HZCY sine omega C T1. Okay, now having achieved this, you are at this position right now, and you have two simultaneous 90-degree pulses that are applied on the proton and carbon channels respectively. Let's take pi by 2 pulse along X for proton, and just for an instance, we can think about this carbon pulse being applied along the Y phase. Therefore, what you're going to have, pi by 2 along X for the proton and pi by 2 along Y for the carbon. Therefore, this is going to end up being 2hy with a negative sign, as z will go to minus y applying x. And then you have a y phase pulse for the cx. Therefore, it's going to be minus cz, so minus of minus becomes plus, cos capital omega c times t1 minus 2hy cy sine omega c t1. So this is immediately after the application of these 290 pulses. That what remains after that is a tau 180 tau module. And the important thing one has to understand here, there are no more 90-degree pulses that are present. Therefore, you realize that there's a multiple quantum term which will not be detectable, and there's only single quantum term that is observable. The reason why this is called HSQC, meaning that the single quantum coherence, is what encodes in the T1 dimension. So for instance, this is what you ended up generating, and during T1 evolution, this results in the frequency labeling of the nuclei that you want to obtain. So therefore, this is a single quantum coherence spectroscopy. So now when you have a tau 180 tau, if you carefully sit and do the math, you will realize that this will refocus, and therefore it will result in something like hx with a cos omega c t1, and this is just borrowed from the previous term. Then you have a t2 acquisition, hx with cos omega h t2. Therefore, we have obtained omega c labeling along t1 dimension and omega h labeling along t2 dimension. It is important to note here the single scan would only give the cos component for the indirect dimension. So repeating the same experiment by changing the phase of the first pulse, that is this pulse, as x and y in two different scans, help you get the other sign part of the signal. This is not an issue for the direct dimension because the hy component would take care of this. However, for the indirect T1 dimension, you need to repeat the experiment in order to get the sign modulation. Overall, this helps you understand how you would be able to generate the complex signal of exp I omega c t1 and exp I omega h t2. Therefore, when you do a two-dimensional Fourier transformation across t1 and t2, you are going to get a signal at capital omega c in the f1 dimension and signal along capital omega h on the f2 dimension. So therefore, these two put together would give you a resonance only if you have the 1JCH that is present. And of course, we have assumed here that the carbon that we are talking about is carbon 13. We're having a carbon 12 1H. This will not be observable. Obviously, because of the fact that carbon 12 doesn't have a non-zero spin quantum number. So therefore, this is exactly how a two-dimensional correlation spectrum is obtained. And when somebody says a carbon 13 HSQC or a 59 HSQC, they imply that such a pulse program is implemented so as to get a two-dimensional correlation between two spins, in this case proton and carbon or proton and nitrogen, resulting in a resonance in this fashion. Another module that's extremely useful is called the heteronuclear multiple quantum coherence spectroscopy. Here, the pulse program is much more simpler. All it has is two pulses on proton, two pulses on the heteronuclear channel, followed by acquisition in proton and decoupling in the heteronuclear channel. Let me once again take the example of 13C1H. And here, the 90 pulses are applied such that this will be the tau delay, and then the 180 pulse is applied exactly at T1 by 2. If you are able to compare this with the HSQC, you are able to understand the number of pulses are much more lesser than the HMQC module than the HSQC. So we will quickly repeat the exercise of doing the density matrix formalism for this case as well. Once again, we'll start with Hz. The first thing is what happens during this duration tau. What are the parameters that are present? You have proton chemical shift, your carbon chemical shift, and you have J coupling. If you pay close attention, in the experimental module, you have tau plus T1 by 2 and tau plus T1 by 2 on either side of a 180-degree pulse. Once again, this is nothing but a tau prime 180 tau prime, meaning that this helps in refocusing proton chemical shift throughout this entire module. So we do not have to worry about proton chemical shift. Since we are starting with Hz, Cz commutes with Hz, so carbon chemical shift will also not evolve in the first tau duration. Hence, the only interaction that will evolve is the J coupling. Actually, I made a small mistake. Actually, this is a small mistake. I am talking about after application of the first pulse, so it will be minus Hy. Nevertheless, all the discussion that we have just made still holds sense. So therefore, if you're evolving this with scalar coupling, you're going to get cos pi j tau plus 2hx cz sine pi j tau. Since you want the coherence to be transferred from the proton to carbon, this is the term of interest, while this is a term that we do not bother about. So in order to make the cos part of the 0 and the sine part of this 1, we set tau equal to 1 over 2j in this case. So if you set 1 over 2j, then what will end up happening is that this goes to 0 while this goes to 1, and therefore you finally get 2hxcz at the end of this portion in the pulse program. The next thing that you're doing is applying a 90-degree pulse only for the carbon channel, and therefore of 2hxcy. And importantly, unlike the HSQC, which had a single quantum antiphase term, here you are able to understand it's a multiple quantum coherence term. Once again, what are all the parameters that could evolve here? You could have proton chemical shift, you could have carbon chemical shift, and you would have the J coupling that could evolve. We just learned a few moments back, it's a tau 180 tau module where the entire proton chemical shift does not evolve in this whole duration, so we do not have to worry about that. And in addition, for a multiple quantum coherence term, we are also aware of the fact that the weak scalar coupling will not evolve. So the only term that will evolve in this case would be the chemical shift of carbon. Hence, the solution for this is going to be minus 2hxcy cos omega c t1 plus 2hxcx sine omega c t1. So we have effectively gone until that far, and now is the time for applying the next 90-degree pulse on carbon 13. So if you're applying along x, cy will get changed to. If you go back to the pulse program, we have now achieved the formalism until this part. You once again see no pulses are present after this final 90-degree pulse on carbon. Therefore, the order of coherence is not going to end up changing. Since this is multiple order coherence, we are not going to be worried about it. The only thing we'll be worried about is this 2hxcz term. Now you have the tau duration for all the reasons that we have just discussed so far. It's only going to evolve with the J coupling that is present, and therefore you would realize this will end up resulting in Hy, where the HXCZ term will refocus to give you Hy, of course, with the indirect dimension chemical shift labeling that has already happened. So this, when let to evolve on T2, will result in chemical shift evolution of the proton, and therefore you would end up getting something of this sort, exp I omega h T2. Of course, you would repeat the experiment again by changing the phase of the first pulse from x to y, and therefore get the sine component of it. And these two signals put together would result in a complex Fourier transformation along T1 and T2 dimensions. to give you a two-dimensional signal once again of the sort that you have seen, omega c in the f1 dimension and omega h in the f2 dimension. So you would realize that the spectrum that is obtained from a HSQC and a HMQC, although looking similar, have their differences that would be present. So let me quickly list out a few differences, HSQC versus HMQC. So the first part is the active term in T1 labeling. Here it's SQ, here it's NQ, which gives the name of the experiment itself. In addition, while this T1 evolution happens, one has to be careful with the kind of terms that are present. For instance, here we just ended up looking for a very simple CH type of a term. But on the other hand, let's say you have a passive coupling. So what is meant by passive coupling? If these are the I and J system, if you have a K coupling that is present, where the K ends up coupling with a proton, you would actually see the passive coupling evolve in the indirect dimension. So what do I mean by that? Let's say you have yet another term which is present in terms of passive coupling, where there is another proton that couples with this carbon, that will end up evolving. So you're thinking of a term such as 2 pi j, let's say Kc, Cz, Kz. Although you were effectively recoupling the Hz term that is present, there are cases where the passive coupling would end up evolving in this duration. So that is a problem in HMQC, which results in very broad resonances or even splitting that is undesirable. No such problems exist in the HSQC. In addition, I'm sure you are able to appreciate the number of pulses is less in the HSQC while it's more in the HSQC. This is advantageous in the fact that the HMQC is a little more forgiving in terms of imperfections that come up in small miscalibrations that you have made in the pulse program. On the other hand, since you have more number of pulses, if you are miscalibrated, then the HSQC is going to give you a lot of phase artifacts on the serious hit in the sensitivity. The final pulse program that I'm going to leave you with today is called the HMBC experiment. This is nothing but heteronuclear multiple bond coherence experiment. So we have just seen an experiment where if the carbon is directly attached to a given proton, we will be able to get this spectrum in the HSQC or in the HMQC. But on the other hand, let us say you desire to correlate this proton to the neighboring carbon, and of course this will also get labeled to the neighboring carbon. This experiment is called the HMBC. This is extremely helpful in the cases where you're trying to assign a significantly sized molecule where the carbon chemical shifts provide you additional resolution. But in order to see who are whose neighbors, the HMBC experiment is extremely handy. So the pulse program goes very similar to the HMQC, where you start from the proton, then you do a tau duration such that the multiple quantum coherence term is generated. You have a short delay, which is tau prime, where carbon-carbon scalar coupling evolves, and following that you have the 180 module, T1 by 2, T1 by 2. Then you get the information back on the proton, acquire along T2. Although you might be a little confused, just for the sake of simplicity, you don't have to worry about proton chemical shift evolution the entire duration. Although I'm ready to accept that it's not even on both sides, we'll discuss later why that is the case. And the other point that you have to keep in mind is that now you have two carbons, let's say C1 and C2, where you have H1 to start with. H1 couples directly with C1, but you want to transfer from C1 to C2. So therefore, there is also a CZ and C prime Z scalar coupling that will be present, which evolves during this duration in order to transfer the coherence. So I suggest you guys to look into the density matrix formalism for the HMBC experiment, which can be discussed during our class.